We will start discussing on uh, breeding methods to handle segregating the materials. That you have pedigree method, backcross method, bulk method, and modifications of these base methods. So the first we'll discuss on the backcross breeding. Then we'll go for the pedigree method next. So backcross breeding, a cross between a hybrid and one of its parent is known as backcross. Hybrid and the progenies in the subsequent generations are repeatedly backcrossed to one of the parent. So what is that repeatedly backcrossed is known as recurrent parent or recipient parent. So genotypes of backcross progeny, they become increasingly similar to that of the recurrent parent, which you repeatedly use it for backcrossing. The progenies will become similar to that repeatedly used parent. So you have in the backcross breeding, you have got a recipient parent and another is the donor parent. So if you cross the recipient parent or nothing but the recurrent parent, which is the donor parent, or it is nothing but the non-recurrent parent, you'll get the progeny that is F1. And then you have to go for subsequent F1 with the recipient parent or recurrent parent. This is to transfer one or few characters from donor parent to recurrent parent. So few genes are there in the donor parent. Maybe one gene, it's good, easy. More genes, that becomes difficult. So that one gene has to be transferred to this recipient parent. So this is to transfer one or few characters from the donor parent to recurrent parent. The recurrent, the requirements for this backcross method are suitable recurrent parent should be available, right? You have to decide that recurrent parent is quite suited. That means it's a standard variety of already existing popular. And then similarly, some characters, one character or few characters are lacking in that recurrent parent. So that lacking character gene should be there in a donor parent. So that means suitable donor parent must be available, having a required character, which are lacking in the recurrent parent. And then you should also have the, the character which you want to transfer should be highly heritable. That means it is controlled by one or very few genes. So then you need to have sufficient number of backcross generations to recover that recipient parent completely. Okay. So what are the applications of this recurrent, backcross breeding? That is, this can be used to intervarietal transfer of simply inherited characters from one variety to other variety, or intervarietal transfer of quantitative character, but it becomes difficult if the number of genes increase more. That quantitative means polygenic inherited character. It becomes quite difficult. And it can be also used to transfer interspecific transfer of simply inherited character from one species to other species. Also, you can transfer, but here not quantitative character, but here it is simply inherited or maybe controlled by one or few genes. Then it can be also used to transfer cytoplasma from one variety or a species to other. So the recurrent parent to which the cytoplasma to be transferred should be used as a male parent. Okay. And the donor parent from which the cytoplasma has to be transferred should be used as a female parent. Very important. This is right. That means the cytoplasma of this donor parent, you are trying to accumulate all the nuclear genes of the recipient parent. So your genotype is going to have all the nuclear genes of the recurrent parent and the cytoplasma of the donor parent. So you need 6 to 8 backcross generations to get the complete nuclear genes of recipient parents into the under the cytoplasma of the donor parent. So it's minimum required. Then this can be also applicable for getting the transgressive segregates. So you need to go for some modifications in the backcross method. After one or sort of 3 backcross generations, you have to go for selfing, so you can get the transgressive segregates. So what do you mean by the transgressive segregates? The the progenies which falls outside the range of the parents, known as transgressive segregates. So to get the probability of getting these transgressive segregates, you can also go for 2 or more recurrent parents you have to use. That means other than the parent which are used, you have to change the parents. So the chances of getting the transgressive segregates will be high. Then it is also going to be useful for production of isogenic lines. So what do you mean by the isogenic lines? So isogenic lines means the two lines, they are similar in all the genes except one or few genes, right? Example will be male sterile female line and the maternal line. So both these A line and B line, A line you call, right? A line is the female parent, which is male sterile, and B line is the maintainer line, which is similar to A line except the male sterility. So A line is male sterile, B line is male fertile. So A and B are ditto except that male sterility. Okay, so that is an example. Like any two lines, if you take and they are similar in all the genes except one or two, are referred as isogenic. So you can use the backcross breeding for that. Then the general procedure to transfer characters is controlled by a single dominant or recessive gene. A single dominant, you do it, it is simple. Whereas if you want to transfer the recessive gene, it is a little bit complicated and it is referred as the modified backcross. Just look at here how the flow of your activity goes with this backcross breeding. First generation, crossing the non-recurrent parent with the recurrent parent. So recurrent parent is, for example, let us take one gene you want to transfer from the donor parent. That is a dominant gene. That means, for example, if the disease resistance is controlled by a dominant gene, so that you want to transfer it from the donor parent or non-recurrent parent, or capital R, right? So this recipient parent is having all the desired character except this gene, which is susceptible to disease. One disease we are taking example. But if you cross these two, dominant recessive, I mean homozygous dominant and homozygous recessive. These two, if you cross, you'll get a heterozygous in F1. This F1 plant. So this F1 plant will be crossed with again a recurrent parent, right? So having a homozygous recessive gene. Now, once you cross this is producing two types of gametes, capital R and small r carrying gametes. And this is producing only one type of gamete, that is small r carrying gametes. If you have the male and female gametes union and formation of the zygote, you got dominant allele and recessive allele heterozygous. Recessive allele and recessive alleles, it is homozygous recessive. So this particular plant will show that this is susceptibility. You are going to reject it, right? Only this plant you are going to select for again backcrossing with the recurrent parent. So again, when you cross this heterozygous with the homozygous recessive, you'll get both the types of parents. One is susceptible to disease, another is resistant. So susceptible is homozygous recessive, resistant is going to be the heterozygotes. So this heterozygote you are going to cross with again the recurrent parent, which is carrying the homozygous recessive. So this is backcross 2. Then if you again cross, you get the backcross 3 generation, right? BC3. Same thing you are continuing. BC4, you will get the same like homozygous recessive and the heterozygote. This again crossed to get the BC5. Same thing you will get. So BC6, again you are going to cross. In BC5, you are going to cross the heterozygote with that recurrent parent. You will get the BC6 generation. That is again giving you the homozygous recessive and heterozygous plant. And now here, okay, the 6 backcross generation means more than 94% of the genes you are getting it from the recipient parents in the progenies. So I think that will be sufficient. You can stop this backcross generations and you can go for selfing. So here you are selfing. So selfing, because it's in heterozygous, this you are rejecting, this plant you are selfing. That means both male and female gametes from the same plant, both are producing, 2 types of gametes. one gamete with the dominant allele and another gamete with the recessive allele. Zygote formation or possible combinations of male and female gametes. You'll get three different types of genotypes. One is homozygous dominant, another is heterozygous, and the third one is the homozygous recessive. This homozygous recessive is disease susceptible. You are rejecting it, right? You're culling this plant, and you are not sure that which one is carrying the recessive allele. Both are showing the resistance, but you don't want to carry forward this because it is going to segregate. So now for identifying these two plants, these two types of plants, you have to go for progeny test. That means individual plants are selfed and grown in a separate progeny rows. So in any row, if that particular row is not showing any segregation, that means this is from this plant. If this plant, the self progeny rows are there, then definitely there will be segregation. Few plants will be resistant and few plants will be recessive. So such progenies, that is derived from this heterozygous, you are rejecting. You are going to select only this capital RR. That means homozygous dominant RR. That means this is having the disease resistance. So this plant is selected. If BC6, once you self, it becomes a F2 generation. And again, if you self it here, progeny row after, you are carrying forward this. This is BC6 F3. So RR plants are selected here after the progeny test. You are doing it here. Then yes, it is now ready. Because its recurrent parent is well-known variety. It is lacking only in that disease resistance, and you do not have to go for extensive yield trials. Just replicated yield trial, multiply the seeds, and you can release the variety. This is simple if it is controlled by a dominant gene, right? The desirable character is controlled by a dominant gene. If it is controlled by a recessive gene, then it becomes quite difficult. We'll see this illustration. And that is referred as a modified Backcross breeding. Recessive gene. So first season or first generation, you are crossing these two parents. So now here, the non-recurrent parent, donor parent is having the recessive gene. Because of this recessiveness, your disease resistance. Some disease resistance are controlled by recessive genes. We say we get example. What many examples? So if you want to transfer this, this is there in some wild species or some other parent, but this is our recurrent parent, which is standard variety, having all desired characters except that disease resistance. You want to transfer, but because that disease resistance is controlled by recessive allele, you have to get it from the donor parent. So this non-recurrent parent. You are going to cross these two, and you will get the homozygous dominant, homozygous recessive, and homozygous dominant. Same one type recessive allele having gametes and dominant allele having gametes. It is fertilized to form the zygote, which is heterozygous. And this heterozygous is nothing but your F1. It is crossed with your recipient parent, carrying the dominant genes. When you cross, you will get the plants, the progenies, two types. One is, this is producing two types of gametes, capital and small. This is producing only capital. This is dominant. So you will get dominant into dominant homozygous, recessive into dominant allele heterozygous. So now you cannot go for backcrossing. Don't know if you backcross with this plant, it's of waste. So for that, the modification is there. Both these plants are susceptible to disease. None of these plants are showing resistance. So here you had to go for selfing. So BC1 selfing means BC2, BC1, F2 it becomes. BC1 this is, and if you go for selfing, it will become BC1, F2. So now once you self this, what will happen? This will produce only this type of plants. So that is rejected. And if from this plant, some plants, all the three types of genotypes you will get, these two phenotypes are susceptible to disease. Only this is resistant to disease. You have to retain this plant and you have to reject these plants. So here these selected plants will be backcrossed. So now you are going for the BC2. Okay. So you are going for the second time backcrossing. So this here, this is heterozygous. You are sure that allele is there, your desirable allele is there. You are going to go for the third backcross generation. So it is crossing. So it is going to give you the same you know, when you cross homozygous dominant and heterozygous, you will get again these two types of plants, right? So you will get the homozygous dominant and heterozygous plants. So in the BC3 generations. So what you have to do, you have to go for selfing. You don't know which one is this and which one is this plant. Morphologically, phenotypically, both are searchable only. So you have to select this and reject this. It is not possible. So for that, you have to go for selfing. If you self, you will self randomly. You get any plant. So plants from which your self seeds are there, rows, all are susceptible. And if this plant self seeds you raise, you will get all three different types of genotypes. And these two genotypes are susceptible, and only this is resistant. That means two different phenotypes, this susceptible and this resistant. You are rejecting these and you are selecting this. So this the resistant variety, I mean the progeny, you are going to cross with the recurrent parent again. So it becomes BC4. So again, this is heterozygous, right? So homozygous recessive and homozygous dominant, if you cross, you'll get only heterozygous. So heterozygous again you have to go for the next backcross generation. So you are going to get BC5. So BC5 again, some plants are homozygous dominant, some plants are, because dominant and dominant allele, homozygous dominant, recessive and dominant allele, heterozygous. So again, you have to go for selfing, right? If you go for selfing, BC5 up to it becomes. Now on selfing, you will get some heterozygous and some homozygous dominant. These plants are susceptible, you have to reject, and you have got homozygous recessive. This is resistant, you have to select. So now I think this BC5 only you can go for, and this plant is selected further, and you can go for replicated yield trial, you go for seed modifications. So BC5 means almost, the what is the proportion of when to stop and all? Yes, you have to, right? You have to decide on depending on the, the number of genes that that character is controlled. A single gene means almost more than 90%. The plants will have the, you have received the genes from the nuclear genes from the recipient parent. 90%, more than 90%. So you can go for it. So what is that? By modified backcross breedings, even you are in the 12th generation, only 12th generation, you have got only 5 backcross generations from it. Whereas here it is, even in 10th, 11th generation itself, you have got 6 backcross generations. So that means you can save here, and Australia, if you want to go for further more generations, you have to go for it. Because, what is the attainment of that, all the genes you are recovering. It is nothing but, the homozygosity you are going to get. Similar kind, you can get in the progenies. So this is what the backcross breeding and modified backcross breeding procedure you are following. As I said, this is modification. You need more time, right? It's complex because of the resist gene is controlled by resist gene. That, I mean, the character resistance is controlled by a residue. The merits of backcross methods. We'll discuss on the, how many generations are required, or how many to get that homozygosity or the complete genes recovery from the recipient parent later. So merits of backcross method: improvement in existing standard variety, you can do it, but that one character is lacking, you have got it from the donor parent and have improved that variety. No need for extensive yield trials, because already the standard variety is known. It is already tested one to release variety, except that character which you are transferring. So no need to go for the extensive yield trials. And you may need the smaller population compared to pedigree method, because only one character you are looking at here. Defects can be overcome. Any 1 or 2 characters are there that can be eliminated by this backcross breeding and selection. This is the only conventional breeding method for interspecific gene transfer, right? So from one species to other species, this is the only method. Cross compatibility and other issues can be there. Then the demerits: new variety cannot be superior to the recurrent parent except the character transfer. That means It is only that additional characters. Otherwise, it is same as that standard variety I started with. So undesirable genes closely linked from maybe also get transferred to new variety from that donor parent, right? A lot of difficulties Charles M. Rick got while going for backcross breeding in tomato to transfer this processing or shelf-life extension characters, because all other undesirable traits from wild species came in. So that's always there. You have to be careful in eliminate such things. Otherwise, it is difficult. Hybridization has to be done each and every generation, or selfing or hybridization, you have to do it, and it is cumbersome. So by the time backcross program over, recurrent parent might have been replaced by some other variety. So that standard variety, you said it right, to which you are transferring only this register. It is now some other varieties are there with better characters. All other characters, better characters. So that means it will be, it will go waste. Or okay, if only addition of the disease resistance only we can make this variety to rule, it's all right. Otherwise, it's a demerit. By the time backcross program over, recurrent parent might have been replaced by other superior varieties. What are the achievements? Quality traits in tomato, like the CM Rick, as I was telling you, a lot of material developed in tomato with the help of those processing, in the help of the wild species. Downy mildew and virus resistance in lettuce, powder mildew resistance in capsicum bacatum, that powder mildew resistance to transport to capsicum annum, then TLCV in tomato. So many activities are, plenty of examples you get it, but when variety released, might be some other method they followed, they may not mention that method. Otherwise, a lot of developments are there. Yeah, I was talking about when you will get the homozygosity and how many backcross generations are required. Well, this, it depends on the number of, the heterozygous genes, or number of genes you have got, and what proportion of homozygosity we are going to get. That, it's going to help you to decide when to stop, or when you are satisfied with what percentage of homozygosity it has been got, and you have recovered that recurrent parent. It is the formula 2 to the power m minus 1 divided by 2 to the power m 2 raised to n into 100. That will give you the proportion of homozygosity in percentage, where m is number of backcross generations and n is the number of heterozygous genes. For example, if one gene is there, so single gene. So that's the first backcross generation, how much? 2 to the power 1, 2 to the power. 2 to the power 1 is 2, 2 minus 1 is 1, 2 to the power 1 is 2, right? So 1 divided by 2 into this number of, the heterozygous pairs is single gene we have taken. 1 divided by 2 means 50% of the, percentage of the homozygosity you get, right? So that is what, if you try, if you use one gene, right, the backcross generation. So the first backcross generation, 50%. 2 genes, sorry, the second backcross generation, number of, the heterozygous gene pairs, if you use, that is, I said it is now you are going for the next generations, right? So n is nothing but your number of heterozygous pair of genes you get. So if it is one backcross, I'll tell you, it's just, yeah, one gene, first backcross generation 50%, second backcross generation 75%, third backcross generation 87.5%. Even selfing also doesn't matter. Selfing also you'll get the same percentage, and the fourth backcross 93.75%, fifth backcross 96.87, sixth you'll get 98. You look at here, the modified method we have stopped at fifth backcross generations, 96%. The genes got into the homozygosity, right? That is, you are recovering that much from the recipient parents. Sixth backcross you got 98%. Seventh, if you go 99%. Eighth, if you go 99.6. Okay, so that means when you can stop, you can decide on. And if the number of genes are 2, right? when the number of genes are 2, and you see number of genes 2, then first backcross generation it is only 25%. For example, 2 genes means uh, what will happen is if it is a single in the for example, if you just take it n is equal to 2, right? The first backcross generation, it is 2 to the power 1, 2 to the power 1. It's 2 minus 1, 1. 2 to the power 1 means 2. 1 by 2, it is 50. I mean 1 by 2 in raised to the power n instead of n 1. 1, it was 1 divided by 2 only. If it is 2, 1 to the power 2 is 1 only. 2 to the power 2 is 4. 1 divided by 4 it becomes. 1 divided by 4 into 100, it becomes 25%. Okay. So first backcross generation, 25%. For the second backcross generation, it is 56%. Third backcross, 76. Fourth backcross, 86%. So like that, if the number of genes are more, you have to go for more number of backcross generations. And again, the modified method to achieve those backcross generation, you need more generation. I mean, more seasons rather. So this will help you, when to stop. You are satisfied with the recovery of that recurrent pair. Okay. So this is what, the how you are going to. It is not only deciding in your, the pedigree method also. It will help, to attain the homozygosity, percentage of homozygosity you are going to get the genes in the plant, and similarly, the number of backcross generations, how many you have to go for to get that. Okay, so so the number of plants necessary in backcross generation is dependent on number of genes involved in controlling the target character. That is very so diploid species, if 2 genes are there, that they're segregated 9:3. We said it, of course, we just mentioned some will be, resistant and some will be susceptible plants. So that is because, single gene we have taken example. If you take 2 genes are controlling that disease resistance, now this is the the segregation ratio 9:3:3:1. So F2 ratio you'll get whenever you go for, provided there is no linkage and no epistasis. Again, if linkage or some interference is there, the ratio will alter. So you just look at this, the number of genes in segregating. How many genes are segregating? One gene, types of gametes produce 2 types gametes, one dominant, one recessive. And the number of different genotypes in F2. So one is homozygous dominant, and second is the heterozygous, and third is homozygous recessive. 3 different types of genotypes will get. Smallest perfect family, you give equal opportunity for the male and female gametes to unite. So 2 gametes from the male side and 2 gametes from the female side. Again, 2 into 2, minimum 4, right? So that perfect family, that's why you said it. So equal opportunity you get for the male and female gametes. So 4 is the minimum number of plants are required. Smallest perfect F2 population is 4 if we have got only one gene controlled character. Number of phenotypes in F2, full dominance is there. Phenotypes means resistant and susceptible. Heterozygous is also dominant, resistant, and homozygous dominant is also resistant. So the only 2 types, you will get the phenotypes. If it is not, the dominance, if both of the alleles are having, similarly, like number of genotypes you get, similar number of phenotypes also you will get, right? So then the number of completely homozygous genotypes, one is homozygous dominant, another is homozygous recessive. Only 2 you'll get. If you take 2 genes for the case, so 2 genes means there will be 4 types of gametes produced, and number of different genotypes in F2 genotypes, 9 different genotypes you'll get. I'll show you here just one example. We'll come back to this. Yeah. So 2 genes we have taken. So male will produce dominant and dominant. First gene also dominant and second gene also dominant. So first type of gamete, it is first gene dominant, second gene recessive, second type of gamete. First gene recessive, second gene dominant, third type of gamete, and both genes are in recessive condition. Fourth, similarly, female also produces same kind of gametes. Now, union possibility or giving the equal opportunity for the male and female, so you'll get, the formation of the zygote, right? Homozygous dominant for both. It is homozygous dominant for the first and heterozygous for the second. Now, if you look at this table, how many different types of genotypes is it telling? 9. This is the first one. First and second gene homozygous. Second one is first is homozygous dominant, second is heterozygous. Third is first is heterozygous, second is homozygous dominant. Fourth is first is heterozygous and second also heterozygous. Fourth type of genotype. Then the fifth one, first is homozygous dominant and second is homozygous recessive. And the sixth one, first is heterozygous, second is homozygous recessive. Sixth one. 7. First is homozygous recessive, second is homozygous dominant. Then the 8th type of genotype you'll get, first is homozygous recessive, second is heterozygous. And the ninth is homozygous recessive for both the genes, right? Ninth is homozygous recessive for both the genes. Okay, so that means 9 different types of genotypes you have got, right? 9 different types of genotypes you have. Now the smallest perfect family, 2 genes when you take, how many plants are required? 1, 2, 3, 4, 4 into 4, 16, right? It is perfect. If you miss one, this is only one plant you are going to get like this. This is only homozygous recessive, only one. Okay, and similarly, homozygous dominant is also only one. So that means for both genes, that means minimum 16 plants are required to recover the any plant. So that's why it is smallest perfect family 16. So number of phenotypes in F2, full dominant. So when it is full dominant, you have got only 4. This 9, 3, 3, 1, we said it, no. So only 4 types. What is that? It is the homozygous dominant and heterozygous are same. Right? Homozygous dominant and heterozygous are same. 4, I said it. Both genes advantage is there. Dominance is there. This is 1. And only first gene advantage, dominant, and second gene is recessive, the second one. Okay. And the third one is first gene recessive, second gene is dominant. Advantage is there. Because what we say, this homozygous dominant and this heterozygous is same. Same type of phenotype you are going to get. This is also same type of phenotype you get. So this is going to be the third phenotype. And this is the fourth phenotype, homozygous recessive. For example, if you take, the disease resistance and you take, or if it is controlled by both genes and the high level of resistance is there, that is this one. And moderate is this, because second gene is not in dominant condition. And the third one is also this. Of course, it depends on what, how the individual genes are. And both the genes advantage is not there. It is susceptible, complete susceptible plant. Like that, any character, if you take to explain, you can make the groups. Okay, that's the phenotypes. 4 different phenotypes. If complete dominance is there. If no complete dominance, similarly, whatever the genotypes are there, the 9 genotypes, different types, no dominance, 9 different types of genotypes you get. And number of completely homozygous genotypes. How many different, the homozygous recessive and homozygous dominant, we said 1 gene. Now in 2 genes, the completely homozygous, there are 4, right? What are those 4? Completely homozygous. This is 1, okay? Completely homozygous. This is 2, completely homozygous. This is 3, completely homozygous. This is the 4th, completely homozygous. Other than these 4 plants, no other plants are completely homozygous. Okay, so that's what we meant for that. So like that, if you take 3 genes, this is the number you will get. So 8 types of gametes you will get, 3, and number of different genotypes in F2, 27, smallest perfect F2 population 64, number of phenotypes in F2, full dominance 8, no dominance 27, Number of completely homozygous genotypes, it is 8. So now like that you can work out, but human brain cannot identify if you go beyond 3. But yes, mathematically it is possible. You got a formula here. Number of genes if you take n, then the types of gametes produced is 2 to the power n, and the number of different genotypes in F2 is 3 to the power n, and smallest perfect F2 population is 4 to the power n. The number of phenotypes in F2 is 2 to the power n when full dominance, and no dominance is the 3 to the power n. And the number of completely homozygous genotypes 2 to the power n. Yeah, this is what already I explained, but the ratio, genotype ratio, if you look at here, that's what I just wanted to mention. This is the genotype means it is a different. There are 9 genotypes, right? 9 different types of genotypes. This is the first one, homozygous for both the genes. Only one plant is there. Now, first gene homozygous dominant and second is heterozygous. These are the only two. Okay. Third, it is the first gene heterozygous, second gene homozygous dominant. Okay. This is 1. Sorry. This is 1, and you have got same plant here. Right? These 2. So there are 2. And now the third one, this is the third one, and the fourth one is, it is heterozygous for both the genes. 1, 2, 3, 4. So that's why the ratio is 4. Okay. Heterozygous for both the genes, 4. And then the fifth one, it is first gene homozygous dominant, second gene is homozygous recessive. So only one plant you will get. Okay. Now the fifth, that is the sixth one. First gene is heterozygous and second gene is homozygous recessive. This is 1 and this is 1. Okay. So 2. Right. And then 2. Then the that is okay. Homozygous sixth one, and the seventh one, first gene is homozygous recessive. Second gene is in homozygous dominant. You have got A, B, where it is only here. So the ratio is 1. And the homozygous recessive for the first and heterozygous for the second, 8th type of genotype, there are 2 plants. So 2. And then homozygous recessive for both the genes, it's 1. So now all the 9 different genotypes you will get. What is the ratio? 1:2:2:4:1:2:1:2:1. So totally 16 plants out of 16. That's the perfect family. So this is what the 9 different genotypes. The ratio you are going to get. Okay, how you have to. If it is dominant, you say complete dominant is there. 9:3:3:1. 9 plus 3 plus 3 plus 1 is equal to 16. Okay, that's what you are going to get. Now I think digenic ratios, if you consider, as I explained, it is 9:3:3:1. A and B are independently expressed. There is no epistatis, there is no interference, and there is no partially dominance or anything. F2 segregation of the parents, we said it's A, B, B, when you F2, that means these 2 plants are homozygous dominant for both genes and homozygous recessive for the both genes. If you cross, what you are going to get, I think this is already explained the same thing, whatever, right? So you will get 9:3:3:2. How you will get 9:3:2? So this is because of complete dominance. The first gene advantage. Advantage means it's dominant. Okay, first gene and second gene, both genes advantage. How many plants are there? 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 9 plants are there. A, second allele, whatever it is. B, so first allele it is dominant, second allele whatever, because it's dominant. B, first allele dominant, second allele whatever it can be. So like that we have chosen 1, 2, 3, 4, 5, 6, 7, 8, 9 plants. Now first gene advantage is there, second gene is there is no advantage. It's homozygous recessive. So how many such plants are there? Second type. So it is first gene advantage there here, not second gene. Okay, here also and here also. There are 3 plants. First gene advantage there. This is the second phenotype, second type of phenotype. And the third type of phenotype where the first gene advantage is not there, whereas second gene advantage is there. So it is this first gene homozygous recessive here also, here also, here also, and second gene here it is homozygous dominant, but since it is a dominant, the heterozygous is also having the same kind of phenotypes. So 1, 2, 3 plants are. So that's why it is 3. The homozygous recessive for both the genes, that is going to give you the another kind of phenotype. It is 1. So 9:3:3:1. Any character if you take, you will get this kind of ratio, and that is very useful for the breeder to make selections or whatever, to decide on the the Backcross or to decide on the population size is going to be useful. So I just telling you deviation from the 9:3:1. That is the one example we said it. If you take anything controlled by 2 genes, if there is when you go for individual plant with the breeding, individual crop breeding, tomato or brinjal or capsicum, you will get the examples for all that, right? Whenever you get. So deviations, that is because of the interaction between the non-allelic genes, that A and B are interacting. So first kind of that is called epistatis, right? Non-allelic gene interaction is nothing but it's epistatis, whereas allelic gene interaction is dominance and recessive, right? The non-allelic gene interaction is epistatis, and how many? You take, we are taking only 2 genes into consideration, not the third or fourth. Leave it. Only 2 genes we are taking, and we are explaining this. So what kind of the epistatis are there? So first is a duplicate recessive gene or a complementary gene. So is this a kind? So what is that? We get okra also. You'll get this YBMB resistance in some of the breeding programs where the source of resistance, it depends. If both the genes are having at least one allele dominant, you will get resistance. And if either of the genes you have got homozygous recessive, the plant will be susceptible to that YBMB. Okay, so what does that? It means homozygous recessive is epistatic to heterozygous, and for the first gene, homozygous recessive of the second gene is epistatic to second gene, heterozygous, right? So if both the genes are in at least one allele in dominant condition, then only the plants will be resistant. So that's why it is called duplicate recessive, right? It is epistatis means duplicate recessive. Otherwise, why it is called complementary? So both genes are complementing each other. If both the genes are there, you will get that final reaction. Both the genes in dominant condition, at least one allele, you will get the positive effect, that is resistance, right? A and B. So how many such plants you will get in? When this is selfing of F1, right? Selfing of F1 after crossing, you are going to make the crosses between the parents, parent 1 and parent 2. Parent 1 is resistant and parent 2 is susceptible. And parent, either of the parent is having the resistant gene. That means homozygous dominant for both the genes. So when you self it, that F1, the male part is producing 4 types of gametes and female also producing 4 types of gametes. Now the possibility of combination of these gametes and forming the zygote and the genotypes you are going to get is, you look at here. We said the condition, but that either of the allele of the gene, if it is there in dominant condition for the both genes, then only resistant. How many such plants you will get here? Here, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9 plants you will get with the advantage of that allele. Both the genes, at least one allele is dominant. So you are getting this. The remaining all are there. So the remaining, at least one gene, if it is in recessive condition, gone. You won't get the resistance. So because of this, you are not getting the resistance. Because of this, you are not getting the resistance. Because of this, you are not getting the resistance. So here also, this is both, right? So that's why you are going to get the ratio. These 3 plants, first category, second category 3, and the third category 1. So 3 plus 3 plus 1 is 7. So the ratio you will get is 7, 9 is to 7. So this is what in Okra you get, or many other examples you can get when you learn about the individual crop breeding. That is duplicate recessive gene, because of the recessive gene is suppressing the expression of other gene. It's having positive effect, or complementary. Both the genes are contributing because of the dominant allele, at least one allele dominant. Now, the second type of epistatis are the interallelic interaction, duplicate dominant genes. So what does that actually look at here? It's a capsula, capsule shape is an example here also. You will get or okay, duplicate dominant genes, how that ratio is 15. Same, the F1, you will get cause the parents, get a F1, F1 is self, you get these types of phenotypes, right? Now, what is that? Here, 15 is to 1. At least one allele is in, at least one gene is in dominant condition, you will get one kind of phenotype. And if both the genes are in recessive condition, you will get the other type. So only two types of phenotypes you will get. So triangular capsule and the top-shaped capsule, you said it. So if, all these plants, genotypes are varying, but the phenotype is going to give you triangular capsule. Okay, triangular capsule with examples. So this homozygous recessive of both gene only will get the top shape. This is a very rare genotype, right? The top-shaped capsule shape of the capsula species. So that is the example for this duplicate dominant gene. What do you mean by the duplicate dominant genes? If either of the genes are having dominant allele, they will give you one kind of phenotypes. If both the genes are having recessive, then only you'll get the other. So duplicate dominant gene action. So duplicate means both genes. At least one allele is in dominant condition, you'll get that. Either of the genes, any one allele is in dominant condition, you will get one kind of phenotype. If that condition is not matched, means the only possibility is both the genes should be on homozygous recessive condition. So that is the other kind of. So only two types of phenotypes, 15 is to 1 ratio you are getting. Okay. The third is recessive epistatics or supplementary ratio, 9 is to 3 is to 4. Mice body color, right? It's now I need not have to explain all that. You can just collect. So C gene, the first gene is a C and the second gene is A. Agouti, banding of individual hair, wild body color you will get, and that is when both the genes, at least one allele is in dominant condition. And if first gene is in dominant condition and second in recessive, you will get colored mice. Okay, that is those three plants. I mean, three rats you will get, and then this homozygous recessive FUT and homozygous recessive for the first gene, you will get albino no color. That means what is recessive epistatic? It is said recessive epistatic. So this recessive gene is suppresses the expression of the other gene. So C homozygous recessive, it will not allow the other gene to express, so it gives albino, no color. I mean white color. So that is 4 plants. I mean 4 rats you will get albino in F2, and yeah, second gene you are going to get is the homozygous recessive. It get color. If both the genes, why it is called supplementary. If both the genes are supplementing, so you will get the agouti body color. Okay. Why it is called a recessive epistatis? Because the first gene homozygous recessive, it is not allowing the other gene to express. It is called recessive epistatics. So the ratio is 9 is to 3 is to 4. Okay. So that is what. So CC mask the effect of AA, recessive epistatics. A supplements C to get agouti color. Okay, that's what. Then the fourth type of epistatis, I think you have learned it. I'm just making refresh your memory. or sometimes you may be under confusion. Dominant epistatics or inhibitory gene action. So this is the fruit color in summer squash, example taken. It's a fruit color. White color you will get when A gene is in dominant condition, at least one allele. And whereas A gene, if it is in recessive and B is in dominant, you'll get yellow. If both genes are in recessive condition, you'll get the green. So three different phenotypes you are going to get. So what is the ratio? 9:3:4. Sorry. So 12:3:1 here. So all this, if you go back to this thing table, you'll get all these plants. I mean the plants, summer squash, you'll get the white. That is 12. So first gene in recessive condition and second gene is in whatever the condition it is. I mean the dominant condition. First gene is in recessive condition, homozygous recessive. Second gene is in at least one allele in dominant condition. You will get the yellow. So those three plants you get. Plus both genes homozygous recessive, green, one plant. So 12:3:1. So dominant epistatic or inhibitory gene actions. So yellow is dominant over the green. Yellow is dominant over the green. So that's why it's dominant epistatic set. So dominant A is epistatic to B. So that is, so dominant epistatic is. Now, why it is called inhibitory? If both the alleles are in recessive condition, it inhibits the color, I mean the other colors, because plants are having the green. So it is referred as dominant epistatic or inhibitory gene action. The ratio is 12:3:1. So all such situations you can encounter. Color development, it's inhibits the color development. They said it. It is it's why it is called inhibitory. Should be clear. A inhibits the color development, means white means its color is not there. Sorry, not the green. A inhibits the color development. Whenever it is A is in dominant condition, it will not allow the color to develop. And if A is in recessive condition, then only color. So again, it's the yellow and green two colors you will get. That is, both genes are in recessive, green you will get, and if B is in dominant, you'll get yellow, like that. So it is A is the dominant allele which is suppressing the color development. It is called as the inhibitory gene action. And dominant epistatics, as I told you, that is the either of these genes, in dominant condition, you will get one kind of the category of phenotype, that is the white color, and remaining all other is not that. Like that, you can explain these terminologies are used. Doesn't matter. It's 12:3:1. What ratio are you getting? So and then one more type of epistat is dominant and recessive interaction. 13:3. A full feather color, that is the poultry bird. That's you will get the feather color. AB, you will get white, and that means A, if it is there, dominant condition, you will get white color. And B, if B gene is in dominant condition and A in recessive condition, you will get the color. Because the ratio they got 13:3. So it's what morphologically you observe, and then you try to interpret what kind of the genetics is operated there. Remember, always if you look at the F2 segregation, you can start looking at what kind of genetics is involved here. So A, it is a dominant and recessive interaction. It is said, right? It is recessive when AB both are there. You will get the white, or because of the dominance of this A gene also you will get the white color. Look at here. So that means both dominant and recessive interaction is there. So B, if it is dominant, and A, if it is recessive, then only you will get the color. So the A is the color inhibitor, right? That's why you will get A is the color inhibitor. Entire thing, all the three. You will get no color. And B, color dominant to white. but B expresses when A is in recessive condition. That's the one thing. It dominates right. You get B will get you the color, but it expression is there when B expresses when A is in recessive condition. Okay. So here B cannot express because it's in recessive, but here B expresses because yes, it is dominant, but condition is A is in recessive condition. So this is called dominant and recessive interaction. The ratio, if you look at 13 is to 3. So right, all 1, 2, 3. This is also in what here? 13. So this is 3, right? The color you get. So out of 16 birds, they got 13 birds color. I mean the white color. Whereas only 3 they got the colored folds, feather color. So that is the type of epistatis, dominant and recessive interaction. A does not allow the B to express. So then one more epistatis, duplicate gene with the cumulative effect, 9:6:1. That again the fruit shape in summer squash. Duplicate gene with a cumulative effect. AB. Yeah. You will get A and B both in dominant condition, at least one allele in dominant condition. This shape of this summer squash you will get. Right? It's this shape. Spatypen you have seen, right? This shape of fruits are there. And when you have got either of the genes in at least one allele dominant, you will get spear shaped. Either A should be in dominant allele, at least one allele dominant, and B at least one allele dominant. That means here this is 3 and this is 3. You will get the spear shaped fruits. Whereas both the genes are in recessive condition, you will get the long fruit shape. That is only one plant you will get. So 9:6:1. So duplicate gene with cumulative effect. So A and B spear shaped dominant over the long shape. Right? A and B when present together give a cumulative disc shape. So this is how it is explained. Now it's always interesting that what kind of the segregation you have got in the F2, and it is not straight away you will get those, for example, 1,000 plants you have raised. You have to assume whether it is falling in how many different phenotypes are there. Then if 3 are there, you can try to fit with the 9:6:1. If 2 are there, you can try to fit it with 13:3. Right? This fitness, you have to do it. Then you can decide what you have presumed is correct or not. Okay? So different kind of epistatis I have explained. It is duplicate gene with the cumulative effect 9:6:1, dominant and recessive interaction 13:3, and you have got dominant epistatis or inhibitory 12:3:1, recessive epistatis supplementary ratio 9:3:4. Similarly, I got the duplicate dominant 15:1. Okay, 15:1. Then you have got 9:7, duplicate recessive gene or complementary gene. So all these types. So now you are getting how many different phenotypes are there and what is the ratio. Right? You observe in the F2 population, how many plants you have got, 1,000 plants, 2,000 plants, how many different types of plants are there. Okay, whether it fits into this or not, you have to always imagine and assume your ratio, and chi-square test you have to do it. So what I have assumed is correct or not. Based on that only you can conclude what I assumed. As per the chi-square test, you can say yes, this ratio I assumed and it is correct. So it is always imaginary, and then proving your imagination or your hypothesis. Hypothesis is your imagination, right? What kind of ratio and what kind of genetics is involved in that particular character. So that is what actually is going to help you, whether you follow the pedigree method or Backcross method, and kind of epistatis, gene interaction, intergene interaction, between the genes interaction, not the intra-allelic. That means the same gene interaction is not there. That is only dominant and recessive. Here, I have given you the complete picture. I hope you have learned, but you can be confident what is you have believed. So modified Backcross method, the production of F2 and F3 use of different recurrent parents you can follow. So F2, F3, immediately you can change. After backcross generations, you go for simply selfing. You'll get F2, F3. That is the modification. Use of different recurrent parents. First time you use one recurrent parent. After few generations, you use the second. But also you can use some other parent as a recurrent, repeatedly used. So, or first you follow backcross method and then you go for a pedigree method, or change of recurrent parents to generate variation. All these are the modifications of backcross methods one can follow. And there is one more method called double backcross method or reciprocal backcross method. It is one good example where you have to always go through the plant breeding journals, right? So papers which are coming. It is the imagination of the plant breeder and how to solve the issues, if anything, generate the variability, and give the opportunity for getting the better genotype. Okay, so all this you have to think. So double backcross method, reciprocal backcross method, it is known as. Here why it is called, and just one example I'm taking. It's in tomato. Earliness is associated with the small fruits. Whenever you go for the early varieties you want to select, the fruits are smaller in size. So early, and if you go for the late types, you got a big fruit size. You want to have the big fruit size, right? If you want to have the big fruit size in the early types, and also, the early small fruit HS102 is a variety, and the late but large fruit size Punjab. Now you want the advantage of both these. Earliness also you want from the HS102, and the big fruit size you want from the Punjab tropic. Okay, so how this is done, you just look at it. Double backcross or reciprocal backcross. The Punjab tropics and HS variety, small fruits, and this is the large fruits. This is the late, but this is small. You got a F1. One side you go for backcrossing with the Punjab tropics. Okay, Punjab tropics. What is that happening? When you go for early intermediates, you get here in this population, you go for selection for the early maturity because your recurrent parent is the big fruit. It takes care. But what is lacking here? It is the earliness. So you have to go for earliness in this population, in this backcross generations. Other side also you go for backcrossing with the HS, which is having small fruits, but it's taking care for the earliness. But here you have to go for what is lacking here in this, because your recurrent parent is having the earliness, no need to worry about it. But the fruit size is the worry, you go for the selection for the large fruit size. Now, if you at the end of the backcross 3, you have got some good selections, right? So these, right, BC3, you can backcross with F1. BC3 of this, you can backcross with the BC3 of this. And this BC3 can be backcrossed with F1. This has been followed. So that means this progenies are backcrossed with F1, and this progeny is backcrossed with F1, and progenies of this BC3 and this BC3 are crossed, right? So all the different types. Now, if you look at the progenies you get it after these backcross generations and the intercross, all progenies were evaluated and selected. Earliness also they wanted, and large fruit size. So that has resulted into a new variety. They are making selection where they got the early types and also big fruit size. So this is the one achievement. They got it, and the various breeding materials they have developed. Okay, so that's why this example I have taken. So like that, any kind of modifications, those are the only base procedures for the breeding method of backcross, and a lot of modifications you go for depending on your need and objectives to achieve your goals. Okay, so that's the backcross breeding we have discussed, and we will stop it here.